All right, so this section is section 11.4, series of non-negative terms, and my name is Professor Oaks. So let's go ahead and start. So in this section, we're going to start with the integral test. So suppose that the function f is continuous, decreasing, and non-negative on the interval from 1 to infinity. Now, notice that this is a half closed interval where the 1 is included here. So if the improper integral from 1 to infinity of f of x dx converges, then the infinite series sum k equals 1 to infinity of f of k converges. And if the improper integral from 1 to infinity of f of x diverges, then the infinite series sum k equals 1 to infinity of f of k then will diverge. So this diverges. All right, so now let's tell whether each series converges or diverges. So now let's think of this in terms of a function now, right, based on the definitions up here. So we're going to actually define an f of x to be this right here, all right? So 1 over x times x plus 1 times x plus 2. Now notice that we have to find out several things, whether the function is continuous, decreasing, and non-negative on this interval from 1 to infinity. So I can see that f has discontinuities, right, at x equals 0 and x equals -1 and x equals -2. All right, x equals 0, x equals -1, and x equals -2. So what I know then is that none of these are in the interval from 1 to infinity. So therefore, f is continuous on the interval from 1 to infinity. And then if I look at this, I also need to verify again that it's decreasing and non-negative. So just by a simple graph of this function, I know that, all right, let's look at this. From the interval 1 to infinity, all right, just if you're clear on this, then I know that the numerator is always 1, and then if I always actually substitute the numbers that are 1 and higher in for x, I would never get a negative number. So I know for sure f of x equals 1 over x, x plus 1, x plus 2 is greater than or equal to 0, or non-negative, so just greater than or equal to 0 on the interval 1 to infinity. And then I just need to make sure that it is indeed decreasing. All right, so generally, to make sure that it would be decreasing, I would just verify that the derivative is less than 0, but let's just look at a graph of this for a moment. So at 1, I have, and I'm actually going to just quickly go ahead and substitute a whole bunch of numbers just so that you can see what this would look like. All right, so if I substitute in 1, I get like a 6. All right, so, and then a 2, I get a 1/24. All right, so the function looks like this on the interval from 1 to infinity. So just keep that in mind. But if I want to, again, verify that this is actually going to be decreasing, then I can go ahead and find the derivative. So why don't I do that? And here I might actually, in this particular case, I am I want it to bring it up on the screen, but I guess I cannot do that very easily. So I want the first derivative of f of x or y equals 1 over x times x plus 1 times x plus 2. And then the thing that I really want you to notice then is that the f prime of x will be, all right, that's going to be, this is quite a lot. So negative 3x squared plus 6x plus 2 over x squared, x plus 1 squared, x plus 2 squared. And I can see that this part will be positive on the interval from 1 to infinity, but it's a negative here. So that means that this f prime of x is less than 0 on the interval 1 to infinity. So therefore, f of x is going to be decreasing on 1 to infinity. So keep that in mind, that I just verified that this is going to be decreasing and continuous and non-negative on that interval. So now I need to confirm whether the integral from 1 to infinity of f of x dx, whether that converges or diverges. All right. So then that will be equal to the integral from 1 to infinity of 1 over x times x plus 1 times x plus 2 dx. So this is one of those improper integrals that we talked about in the past. So I am going to rewrite this as the limit as b goes to infinity of the integral from 1 to b of 1 over x times x plus 1 times x plus 2 dx. And then I can use partial fractions to go ahead and rewrite the integrand here. So in other words, 1 over x times x plus 1 times x plus 2 will be a over x plus b over x plus 1 plus c over x plus 2. And I'll let you go ahead and find the a, b, and c on your own, but they end up being a is a half, so 1/2 over x, and then b is -1, so -1 over x plus 1, and c is a half, so 1/2 over x plus 2. So then this will be the limit as b goes to infinity of the integral from 1 to b of 1/2 over x plus -1 over x plus 1 plus 1/2 over x plus 2 dx. And then if I evaluate this integral, I have, what do I have? I have limit as b goes to infinity of 1/2 natural log of the absolute value of x minus natural log of the absolute value of x plus 1 plus 1/2 natural log of the absolute value of x plus 2. All of this, evaluate it from 1 to b. So then what do I have here? I have limit as b goes to infinity of, 1/2 natural log of b minus a natural log of b plus 1 plus 1/2 natural log of b plus 2, and then minus the 1/2 natural log of 1 minus natural log of 1 plus 1, then plus 1/2 natural log of 1 plus 2. So then I just go ahead and I simplify here. So what do I have here when I simplify? Well, I have, let's go ahead and figure out what the best way to do this would be. Well, I know that natural log of 1 is 0. So this is just negative natural log of 2 plus 1/2 natural log of 3. And then I'll go ahead and just simplify in here. So I am actually, I think what I'm actually going to do is make this into 2 over 2, so there's a common denominator of 2 here, and then I can factor out the 1/2. So limit as b goes to infinity of 1/2, and then natural log of b minus 2 natural log of b plus 1 plus natural log of b plus 2, and then we have minus the negative natural log of 2 plus 1/2 natural log of 3. So just make sure, like you have all of the parentheses here also. What a time to be alive, right? And then just use property of logarithms here. So let's use some properties of logarithms. So I'll actually go ahead and use the power rule for logarithms to bring the squaring up, and then I'll distribute this negative here. So I have 1/2 natural log of b minus natural log of b plus 1 squared plus natural log of b plus 2. Then we have plus natural log of 2 minus natural log of 3. And then I'm still not done. What a time to be alive, right? So now let's use the properties of logarithms again. So we have limit as b approaches infinity of 1/2. And then we have natural log in the numerator of b. And then the negative here in front of the natural log of b plus 1 squared means that b plus 1 squared goes to the denominator. Then we have a b plus 2. All right, then we have a plus natural log of 2 minus natural log of 3 over 2, or 1/2 natural log of 3. And then I look at what is right here, this part, and I'm going to highlight it since it's getting a little bit messier than I was anticipating even myself here. So this expression, all right, as b goes to infinity, right, that expression is limit as b goes to infinity, 1/2 natural log of, and that will be b squared plus 2b over, and if I multiply that out, b plus 1 times b plus 1, b squared plus 2b plus 1, and then plus natural log of 2 minus 1/2 natural log of 3. But as b goes to infinity, this goes to 1, so we have, this is natural, or 1/2 natural log of 1 plus natural log of 2 minus 1/2 natural log of 3, but natural log of 1 is equal to 0. So this is just going to be natural log of 2 minus, well, that's 1/2. All right, 1/2 natural log of 3. And so the integral converges. So therefore, since the integral converged, that means that the original series that we were examining also converges. So in other words, since the integral converged or converges, this series also converges. And that is the integral test. So I really hope that you enjoyed the integral test. And now it is time for another great example here. So let's do another example here. And it is this series right here. the sum k equals 3 to infinity of 1 over k times natural log of k times natural log of k. So what I'm actually going to do is I am now, by the way, I just want to be clear on one thing here, that I hope that it's clear to you that I couldn't start at k equals 1 here, because that would put natural log of 1 in the denominator, which would be 0 in the denominator here. All right, so we're going to work on the interval from 3 to infinity here. So that's what we're starting at. So let's start similarly to the last one. So let's define f of x equals 1 over x, natural log of x, natural log of the natural log of x. And then you can verify that f is, I'll let you verify this, but f is continuous and decreasing and non-negative on the interval from 3 to infinity. So let's set up our limit now. So the limit as b goes to infinity of the integral from 3 to b of 1 over x natural log of x natural log of the natural log of x dx. And let's just use a simple u substitution here. So I'm going to let u be the natural log of the natural log of x. So what does that mean for us here? Well, du is 1 over the natural log of x, and then times 1 over x dx. So this integral is just the indefinite integral is just 1 over u du, which is natural log of the absolute value of u plus c, or natural log of the natural log of the natural log of x plus c. All right, so now what are you going to do with that information? Well, that means that this improper integral is just now the limit as b goes to infinity of, let's see, so this is limit as b goes to infinity of the natural log of the natural log of the natural log of x, evaluated from 3 to b. So now if I do this, I have a limit as b goes to infinity of the natural log of the natural log of the natural log of b minus the natural log of the natural log of the natural log of 3. So, well, this first term here goes to infinity as b goes to infinity. So therefore the integral diverges, and so the series sum k equals 3 to infinity 1 over k natural log of k natural log of k, right, that also diverges. So I hope that you enjoyed that example of some series with the natural log. And now it is time for another great example today. So here we have the sum n equals 1 to infinity of, and that, yeah, so of n over n squared plus 1. So let's, similarly to the last two, define an f of x just to be x over x squared plus 1. And I'll let you verify that f is continuous on 1 to infinity, so continuous, decreasing, and non-negative on 1 to infinity. So now, what do we have here? We have to look at, again, the improper integral from 1 to infinity of x over x squared plus 1 dx. So that's the limit as b goes to infinity of integral from 1 to b of x over x squared plus 1 dx. So this just requires a simple u substitution again. So u is x squared plus 1, du is 2x dx. So therefore 1/2 du is x dx. So this indefinite integral becomes 1/2 integral of 1 over u du, or 1/2 natural log of u plus c, or in terms of x, 1/2 natural log of x squared plus 1 plus c. All right, so then I go back to my original integral over here. So this will become limit as b goes to infinity of 1/2 natural log of x squared plus 1. Evaluate it from, where is it, 1 to b. And if I do this, I have limit as b goes to infinity of 1/2 natural log of b squared plus 1 minus 1/2 natural log of 1 squared plus 1. All right, so this term here goes to infinity. So therefore, the integral diverges, and therefore also the series, the original series, sum n equals 1 to infinity of n over n squared plus 1, also diverges. What a time to be alive, right? I really hope that you enjoyed this example here. All right, so try to enjoy this as much as you can, because now we are going to talk about P series. All right, so P series is coming up next. So what a time to be alive. So what is a P series? This is a series of the form sum k equals 1 to infinity of 1 over k to the p, where p is constant. So when p is equal to 1, the series becomes a harmonic series. Right, so this is a special, harmonic series. So this is a special series that you may have heard about before. It's not like a mini series on TV or anything like that. It's just a series. And P, I really think that you need to be aware that the P is really like for power, because it's representing the power of the K in the denominator here. But just remember that that is our name for it, is P series. In the P series, sum k equals 1 to infinity of 1 over k to the p converges if p is greater than 1, and diverges if p is less than or equal to 1. So in particular, then, the harmonic series diverges. So this series actually diverges. Just so that I'm absolutely clear on that, that series diverges. So let's test each series here for convergence or divergence. So the sum k equals 1 to infinity of 1 over k squared. This is a P series of the form, and again, we're going to write it in the correct form, just like we did for all of the geometric series, just to make sure that we're clear on what the series is, whether it's a P series or a telescoping or alternating or a geometric or whatever it might be, right? I want to try to make sure to write it in the correct form to identify it. So k equals 1 to infinity of 1 over k to p, with p is equal to 2. And then since the p is greater than 1, this series converges. All right, so this one converges. Now if I look at the next one, if I rewrite this series, it's sum k equals 1 to infinity of 1 over k to the 1/3 power, because that's the same as the cube root of k. So then this is a P series of the form k equal sum k equals 1 to infinity of 1 over k to p, with p equals 1/3, And then since p is less than or equal to 1, this series actually diverges. All right, what a time to be alive. I really hope that you are enjoying this video here so far. So now it is time for the next type of test that we're going to do. So we talked about the integral test already. So now here are some of the comparison tests. All right. So how about the domination of series here? So what does domination of series mean? So if you let the sum from k equal 1 to infinity of ak and sum k equal 1 to infinity of bk be two series whose terms are non-negative, then we say that so non-negative terms, the series bk dominates the series AK if AK is less than or equal to BK holds for all positive integer values of K. So now here is the direct comparison test. So if AK and BK are series whose terms are non-negative, and suppose that BK dominates AK, which means again that the series AK's terms, AK less than or equal to BK holds for all positive integer values of K. So we're trying to say that for all of the terms, AK is less than or equal to BK. So if the series BK converges, then AK converges, and if AK diverges, then BK diverges. So let's consider the series sum k equal 1 to infinity of 1 over 1 plus 3 to the k. So I'm going to call this AK. So 1 over 2 plus 3 to the k. And then remember, I'm trying to compare the series. So I'm going to try comparing this to sum k equal 1 to infinity of 1 over 3 to the k. All right, so now I'm going to just call that bk then, all right? 1 over 3 to the k. So I need to show, if I do this, I need to show that the bk, all right, the bk series here dominates the AK series. So 1 over 2 plus 3 to the k. So that means that, in other words, I need to show that for all integer values of k, that AK is less than or equal to BK. So AK was 1 over 2 plus 3 to the k, and BK is 1 over 3 to the k. And how would you know that is true? Well, this is actually a smaller value than this because the limit as k goes to infinity would have this one going to values of 0 faster than that one, all right? So therefore this is clearly true. So now I just need to show whether this BK converges or not, because if it does, then the original series AK converges. But if I can't show that, then I need to show that this just diverges, all right? So just keep that in mind, that this is what I'm trying to do. So I can rewrite this as, well, sum k equals 1 to infinity of 1/3 to the k, and then I know that this is geometric if I write it as 1/3 times 1/3 to the k minus 1. So this is geometric with the absolute value of r less than 1. So that means that the series BK converges. And since the BK dominated AK and BK converges, that means that AK converges. So therefore, the series k equals 1 to infinity of 1 over 2 plus 3 to k also converges. All right, what a time to be alive. So let's try another example here. All right, so let me get another example ready for us. So now we have the sum k equals 1 to infinity of 1 over 2 plus the square root of, and this should actually be k and not n because that's k is the index here. So I'm just going to call this ak, 1 over 2 square root of k. And then I'm going to try comparing this to sum k equals 1 to infinity of just 1 over the square root of k, or sum k equals 1 to infinity of 1 over k to 1/2. And this is a P series with P is equal to a half. And so since the P is less than 1, this diverges. All right, so try to remember this as well. So um, so now, all right, so now we still need to show that so that the BK series, this one, all right, BK 1 over square root of k, k equals 1 to infinity, then of 1 over the square root of k, does that dominate the other series AK? All right, so let's show that today. So we need to show that for all integer values of k, does AK, is that less than or equal to BK? So 1 over 2 plus, or no, 1 over, oh, AK was 1 over, yeah, 2 plus the square root of k, is that less than or equal to 1 over the square root of k? And I think that I can use a similar argument just as before, so hopefully you see that this is again clearly true. So this is clearly true. And so then that means that we can say that the original series AK converges. So therefore, all right, sorry, diverges. Diverges. So therefore, sum k equals 1 to infinity of 1 over 2 plus square root of k diverges. All right, what a time to be alive. So now, hopefully you enjoyed that. All right, so I'll freeze that for a moment so that if you want to write that one down, you can. But now, here we go. So I'll let the sum k equals 1 to infinity of AK be a series of non-negative terms, and suppose that the sum k equals 1 to infinity of BK is a series of positive terms such that the limit as n goes to infinity of a n over bn equals c, where c is greater than 0, then either both series converge or both series diverge. So there's a slightly modified limit comparison test here, but just remember that you can always go back and look on your comparison test and all the other tests whenever you would like by Okay, so for some reason, I thought I only have one copy of this at home, and I have like 50 copies of this, and this is actually a nice one that that I know that I have shown that I have used, that I found on the internet, and here you are watching this on the internet. So that means if you found this video, you should be able to find the other video otherwise, or other videos and other places on the internet where things like this might be located. But in any case, just always remember that if you can't find anything, you should take the power searching with Google course and get certified in power searching with Google. You know, I have my certificate. I think that it's not a bad thing for anything to have, anyone to have, because you know, you never know when you won't be able to get a hold of a private investigator, and you might have to take things into your own hands, right? So just keep that in mind as well. But let me just bring up the fact that this is actually a modified version of the limit comparison test compared to the original statement that was here and here. All right, so keep that in mind as we go through this. So let the sum as k equals 1 to infinity of ak be a series of non-negative terms, and suppose that the sum k equals 1 to infinity of bk is a series of positive terms. So then if the limit as n goes to infinity of the ratio of an over bn is equal to 0, and the series bk converges, then the series ak converges. And if the limit as n goes to infinity of that ratio is infinity, and the series bk diverges, then ak diverges. So the one thing that you need to remember is that, again, this series of non-negative terms, that does include 0. So this includes 0, but positive means that this does not include 0. But the thing is that b was in the denominator, so you don't want there to be a 0 in the denominator. So that's one of the major reasons why we need to be careful of what is going on here. All right. So example 7 here. Consider the sum k equals 1 to infinity of 1 over ak plus b, and that's where a is greater than 0 and b is greater than 0. So I'm going to just call this an. All right, so that's an is 1 over an plus b. So instead of ak, an. And then I need to find a series to compare this to. That's why it's called a comparison test. All right, so I'm going to compare this to sum k equals 1 to infinity of 1 over k, which is a divergent P series, since the P is less than or equal to 1. And in other words, this is just the divergent harmonic series. All right. So then just again, remember that I already know that A is a series of non-negative terms and B is a series of positive terms, because look here, I have my A is greater than 0 and B is greater than 0, so I have 1 over a positive number, which means that this is going to be greater than 0. All right, it doesn't matter that if it includes 0 or not, but it could include 0. Okay, so this right could include 0, but it doesn't have to. Right, in this case, you won't want it to be include 0, because there's a 1 in the numerator, all right, and the 1 over 0 is undefined anyway. So now, if then the ratio of an over bn would be 0, then since this actually by the way, then we would see if bk converges, which we already know it doesn't, but the limit is equal to infinity, then since bk diverges, then the series ak will diverge. So hopefully that's what we're trying to find out here, is that this is what will happen. So bn is just, well, that will be 1 over n instead of 1 over k. So we have limit as n goes to infinity of an over bn, so that's limit as n goes to infinity of 1 over an plus b over 1 over n. So if I multiply by the reciprocal, this is limit as n goes to infinity of 1 over an plus b times n over 1. So then this ends up being limit as n goes to infinity of, well, think about this, all right? This is just n over an plus b, but these have the same degree, so as n goes to infinity, this is just tending toward 1 over a, right? So that is equal to 1 over a, and so then, since the a is greater than 0, and 1 over a is greater than 0, all right, and then since the limit is greater than 0, well, think about this, all right? This means that we couldn't actually use the modified comparison test here, but if we go back to look at what the limit comparison test says, then if this is equal to some value of c, all right, so, well, as long as that c is equal to some number greater than 0, and it was equal to 1 over a, and 1 over a was greater than 0, then that means that both series converge or both series diverge. So b diverge, so that means therefore also a diverges. So by the limit comparison test, not the modified one, but the limit comparison test, both series must diverge. All right, what a time to be alive. So now let's try another one here. So let's consider the sum k equals 1 to infinity of the square root of k over k squared plus 1. So I am going to try to look at a couple of things here that you could try out. So let's say that I just call this an. So that will be, what is it? Okay. Square root of n over n squared plus 1. So I'm going to compare this to, now, by the way, you might actually try to compare to one series, and then you get something that actually, something that seems like it doesn't fit one of the cases. That doesn't mean that you actually can't use the limit comparison test or the modified limit comparison test. It just means that you might need to pick a different series to compare to. All right, so keep that in mind as well. But what I am going to do is just, since I'm just talking to myself here, and I really don't want to go crazy here, I'm just going to jump to one series that I know will work. So now let's try to compare to some k equals 1 to infinity of just the square root of k over k squared. So that's some k equals 1 to infinity of k to the 1/2 over k squared, or sum k equals 1 to infinity of 1 over k to 3/2. And this is a convergent P series, since the P is actually greater than 1. All right, so now what I'm going to do is I'm going to find the limit as n approaches infinity of, now let's just call this, all right, Bn is 1 over n to the 3/2 power. So limit as n approaches infinity of an over bn. So that's the limit as n approaches infinity of square root of n over n squared plus 1 over n to the 3/2 power. I'll multiply by the reciprocal, so that's limit as n approaches infinity of, I'll make that square root into n to the 1/2 over n squared plus 1 times n to the 3/2 over 1. So this is limit as n approaches infinity of, n to the 1/2 times n to the 3/2 is n squared. So n squared over n squared plus 1. And as n goes to infinity, this actually approaches 1. Now, this is a positive and a finite value. So this is a positive and a finite value. So this is actually the same as the last case here, like having a positive and a finite value. Just that in the last case, the last series, we just had 1 over a, but we didn't know what a was. But if we knew what a was, we would know that it was some number greater than 0 that's a finite number, right? But here we have a 1 here. And so since this series that we're comparing to converges, that means both series converge. So therefore, by the limit comparison test, both series converge. Right, so that we see that this series here converges. So I hope that you enjoyed this, because I have another great example coming up here. So we'll do this. I hope that you're enjoying this as well. I mean, I wouldn't normally say that I'm enjoying this, but there's not much else to do outside right now, right? So let's see. Let me go ahead and bring up the next example here. What a time to be alive, right? So now, oh, okay. So now let's consider some n equals 1 to infinity of n times 2 to the n over 4n to the third plus 1. So here is our an, that's n times 2 to the n over 4n to the third plus 1. And now I need to find a series to compare this to. All right, so think about this. I have n times 2 to the n over 4n to the third, approximately, right? Because I don't really care too much about that plus 1. And then if I cancel out an n or divide out an n, this is 2 to the n over n squared. So I'm going to compare this to the sum n equals 1 to infinity of 2 to the n over n squared. And then this is not a P series or a geometric series, but this is divergent by the test for divergence. So this diverges by the test for divergence. In other words, the limit as n goes to infinity of 2 to the n over n squared does not equal 0. So now we'll call this Bn 2 to the n over n squared. So now the limit as n goes to infinity of an over bn is the limit as n goes to infinity of an is n times 2 to the n over 4n cubed plus 1 over bn, which is 2 to the n over n squared. Then just like in the other examples, I'll multiply by the reciprocal. So this is limit as n goes to infinity of n times 2 to the n over 4n cubed plus 1 times n squared over 2 to the n. So the 2 to the n's divide out. So I have limit as n approaches infinity of n times n squared, n to the third over 4n to the third plus 1. And then as n goes to infinity, this actually tends to be 1/4. And this is a value which is positive and finite. So therefore, by the limit comparison test, both series diverge. So both series diverge. What a time to be alive, right? I'm actually getting pretty hungry right now for Chicken Shack again. So I can definitely tell that it's almost lunchtime, but that's okay. I'll stick with you guys here. So now, let's look at the next example here. This one is one of those cases where you see that I've only been dealing with trying to write these series as something that I already recognize, right? So let me take a look at this series right here, and sum k equals 1 to infinity of natural log of 1 plus 1 over k, and let me find a common denominator. So natural log of, let's just write it, k plus 1 over k, and then this is sum k equals 1 to infinity of natural log of k plus 1 minus natural log of k, which hopefully you recall is a telescoping series because it's a k plus 1 minus a k here, or b k plus 1 minus b k. All right, so this is a series which is a telescoping series. So now I'm just going to go ahead and consider then the series of, or the partial sum. So Sn is the sum k equals 1 to n of the natural log of k plus 1 over k. So this will be natural log of 1 plus 1 minus natural log of 1, and then plus, so that's for k equals 1. Then we have natural log, if k is 2, we have natural log of 3 minus natural log of 2. Then if k is 3, we have natural log of 4 minus natural log of 3. Then if we have so on and so forth, right? We have natural log of n plus 1 minus natural log of n. And hopefully you can see the terms that will subtract out: natural log of 2 minus natural log of 2, natural log of 3 minus natural log of 3, natural log of 1 is actually 0. So that means that the only term that will actually be left is going to be the natural log of n plus 1. All right, so this is equal to natural log of n plus 1. So then I need to look at the the limit then, so the limit as n goes to infinity of Sn is the limit as n goes to infinity of the natural log of n plus 1, which ends up being infinity. So therefore, the series, the original series, natural log of 1 plus 1 over k, diverges. Diverges. All right. What a time to be alive. I really hope that you enjoyed this example because I only have 2 more for you today. All right. So here we go. Here's another example. So let's consider the sum k equals 2 to infinity of the natural log of k over k squared plus 4. So now let's look at this one here. So this is my, let's call that an. All right, so natural log of n over n squared plus 4. So I really, again, don't really need to look at that 4 very much. So we have natural log of n over n squared, and that will be approximately the square root of n over n squared, which is then n to the 1/2 over n squared, which is 1 over n to the 3/2. So just try to realize that I am using a trick that I know about for writing a series as a series that I know already, but as you do more and more of these, I think that you'll definitely get a little bit better at this. But hopefully you can see when I say approximately, I do mean approximately, because here was the natural log of x, and there is the square root of x. All right, so one of them is definitely going to be different than the other one, of course. All right, so now I'm going to compare this series to, so compare to the series k equal 1 to infinity of 1 over k to the 3/2, which is a convergent P series since the P is greater than 1. So then I'm going to let the Bn be 1 over n to the 3/2, and I am going to use, in this case, the modified limit comparison test. All right, I'm just telling you that up front. So use the modified limit comparison test. All right, so now limit as n goes to infinity of an over bn. So that's a limit as n goes to infinity of an was natural log of n over n squared plus 4, and bn is 1 over n to the 3/2. Then I'll multiply by the reciprocal, so natural log of n over n squared plus 4 times n to the 3/2 over 1. And then I see that there's a lot of ways to go about doing this. All right, so I am actually going to move this to the denominator. All right, just to make it a little bit easier in the long run for me. So I move that to the denominator as limit n goes to infinity of natural log of n over n squared plus 4 times n to the negative 3/2 power. So that would be limit as n goes to infinity of natural log of n over, if I distribute here, n squared times n to the negative 3/2 power is n to the 1/2 power plus 4n to the negative 3/2 power. And now I am going to go ahead and use L'Hopital's rule, since I see that I have the indeterminate form infinity over infinity here. Now remember, I should write this as like limit as x goes to infinity of natural log of x over x to the 1/2 plus 4x to the negative 3/2. But I'm leaving it up to you to be a little bit responsible for the notation and again know what's going on here. So now, now this should make a little bit more sense to you why I did this, because if I would have used L'Hopital's rule up here, I would have needed the product rule. All right, just keep that in mind. And now I don't need that. So I have limit as n goes to infinity, the derivative of natural log of n, 1 over n, and then I have 1 half n to the negative 1 half plus the 4 times the negative 3 halves. That would be negative 6, so minus 6 n to the negative 5 halves. And then I go ahead and I simplify this. So this is going to be limit as n goes to infinity of 1 over n over 1 over 2n to the 1 half minus 6 over n to the 5 halves. And then what I'm going to do is I am going to just multiply through by n, all right, over n, so n over n, so n and n, just to make this a little bit easier for me, right? So now I will have limit as n goes to infinity of 1 over, well, okay, n to the 1 half over 2 minus 6 over n to the 3 halves. And if you look at what is going on here, then that this actually, as n goes to infinity, goes to 0. This part goes to infinity. So this is like 1 over some really large number, which goes to 0. So what does that mean? It means that if you look at the modified limit comparison test, that if this went to 0 and the series BK converged, which it did because it was a convergent P series, then that means the series AK converges. So therefore, since the, again, series, sum k equals 1 to infinity of BK, or that was the series 1 over k to 3 halves, converges, therefore, that means that both series converge. All right, what a time to be alive. I really hope that you enjoyed this here. I don't have any indication if you're enjoying this, so you'll have to drop a comment in the comment section or whatever is the easiest for you to indicate your enjoyment of this excellent video here on the limit comparison test. All right, and now it's time for another example here. Consider the sum j equals 1 to infinity of j factorial over 2j factorial. So I am going to just call this let's call that an. So that's n factorial over 2n factorial. So I'm going to consider comparing to, oh, by the way, this one is one of those that could get a little tricky, so don't be upset. All right, so yeah, so consider comparing to the sum j equals 1 to infinity of 1 over j squared, which is a convergent P series of p greater than 1. And so what I'm going to do, so with p greater than 1, it's convergent, all right? So I'm going to use the modified limit comparison test again. So then, so this is going to be my bn. My bn will be 1 over n squared. So limit as n goes to infinity of an over bn is limit as n goes to infinity of n factorial over 2n factorial over 1 over n squared. Now I'll multiply by the reciprocal just like usual. So limit as n goes to infinity of n factorial over 2n factorial times n squared over 1. And now this will give me a limit as n goes to infinity of, all right, so here we go. It will be, well, n factorial times n squared, and then 2n factorial. If you remember how this works, it is 2n times 2n minus 1, 2n minus 2, 2n minus 3, and so forth, all the way down to n plus 1, and then I can do the rest of it as n factorial. And the reason why I want to do that is so that the n factorials divide out. And now, what am I going to do? Then I actually am going to divide the numerator and the denominator by n squared. All right, so divide by n squared, divide by n squared. So now I've ran out of paper, so let me find a piece of paper, which I conveniently have right here. All right, isn't that convenient that I didn't have to go chop down the tree or anything, that the piece of paper was already here for me. So that's modern day technology for you. So this is limit as n goes to infinity of n squared over n squared is 1. And then what I'm actually going to do is just be very careful of how this actually works here, right? So then I have 2n over n squared is just 2 over n, then times 2n minus 1, 2n minus 2, 2n minus 3, and then all the way to n plus 1. So not every factor gets divided by n squared, just the first factor here. And then what I'm actually going to do is I am, by the way, like, if you're really concerned about what is going on here, you probably should be. But the reason why I'm doing this, if you haven't realized already, is that n is going to infinity, and I have 2 over n here. So this is actually 2 over 0, which puts a 0 in the denominator. So I need to keep on rewriting this to see if I can get the 0 out of the denominator. So I'm going to distribute this into the first factor here. So I have then 2n. All right, so 2n times 2, so that 4n over n minus 2 over n, then times 2n minus 2 times 2n minus 3, all the way to n plus 1. Then these n's divide out, and then as n goes to infinity, this goes to 0. So then this ends up being limit as n goes to infinity of 1 over, right, 4 times 2n minus 2, 2n minus 3, all the way to n plus 1, which is 1 over some really large number. All right, so then that ends up being 0. And so therefore, since this was 0, then by the modified limit comparison test, the one that I was using here, then since the series BK, so that would be from, or BK, so we had, we used letters J here, so J equal 1 to infinity of B sub J is sum J equal 1 to infinity of 1 over J squared, right? Then that means that this one equals, yeah, this one equals 0, right? So that one was, that limit was equal to 0, and then this one actually, if you look at it, was convergent since it was a P series. So since that converges, therefore both series converge. All right, so that is it for this section on the, well, all of these comparison tests, but more than that, it's the series of non-negative terms. And then in the next section, or in what is coming up, we will talk about what happens when some of the terms are negative, or when there are series whose terms change sign. So that will be when we talk about all of the alternating series that you might also encounter. So I really hope that you enjoyed this video, and feel free to tell everyone about it, and I'll see you next time. Thank you and have a great day.